million miles from Earth, floating in the permanent shadow of its own sun shield, a machine is quietly dismantling the story we have told ourselves about how the universe began. The James Webb Space Telescope does not orbit the Earth. It orbits a gravitational balance point called Lagrange 2, a position where the combined gravity of the Earth and the Sun conspires to keep it steady, cold, and undisturbed. Its mirror spans 6.5 meters, coated with a layer of gold, 48.25 nanometers thick, roughly 1,000 times thinner than a human hair, chosen because gold reflects infrared light with an efficiency that no other material can match. On its sun-facing side, temperatures reach over 80 degrees Celsius. On its shadowed side, where the instruments live, the temperature drops to minus 233 degrees. It has to be that cold. Because the light it is looking for has been travelling for more than 13 billion years, stretched by the expansion of the universe from visible wavelengths into the faint infrared whisper that only the coldest instruments in existence can detect. Before we begin, if you're kind enough, a gentle like and tap on subscribe would mean the world to me. It's a small gesture, but I hold it with deep gratitude, because every bit of your support keeps this tiny universe alive. When the James Webb Space Telescope stares at a region of sky that appears completely black to the human eye, it is not searching for nothing. It is waiting for photons that left their sources when the universe was still a child. Photons that have been travelling through expanding space for so long that by the time they arrive at the telescope's mirror, they carry information from an era so remote that the Sun did not exist, the Milky Way had not yet finished forming, and the atoms that would one day become the Earth were still scattered inside the cores of stars that had not yet been born. Each photon is a time capsule. Each one carries a timestamp encoded in its wavelength. The more the universe has expanded since the photon was emitted, the more its wavelength has been stretched. This stretching is called redshift. And redshift is not simply a measure of distance, it is a measure of time. To look farther into space is to look deeper into the past, and the James Webb Space Telescope was built to look deeper than anything that has ever existed. What it found there was not what anyone expected. For decades, the standard model of cosmology told a clear and elegant story about the early universe. After the Big Bang, space expanded, temperatures dropped, and matter spread out in an almost perfectly uniform sea of hydrogen and helium. Tiny irregularities in the density of that primordial gas, imprinted by quantum fluctuations during the first trillionth of a second of existence, provided the seeds for everything that would follow. But gravity is patient. Dark matter, the invisible scaffolding that outweighs ordinary matter by roughly 6-1, began to accumulate slowly around those seeds, forming halos that grew through gradual mergers and accretion over hundreds of millions of years. Only after these dark matter halos had grown large enough could ordinary gas fall into them, cool, compress, and ignite the first stars. The first galaxies were expected to be small, faint, fragile, primitive assemblies of a few million stars, struggling to hold themselves together in a universe that was still too hot, too diffuse, and too young for anything large to exist. The James Webb Space Telescope was supposed to find those fragile beginnings. Instead, it found monsters. Within the universe's first 500 to 700 million years, an era so early that the standard model predicted near emptiness, Webb detected galaxies that were already massive, not small collections of infant stars, fully assembled systems containing hundreds of millions, in some cases billions of solar masses worth of stars. In February 2023, an international team led by Ivo Laber of Swinburne University of Technology in Australia published a study in the journal Nature describing 6 candidate galaxies discovered in Webb's first deep field images. Each one appeared to have existed when the universe was only 3% of its current age, and each one contained almost as many stars as the modern Milky Way, a galaxy that has had 13.8 billion years to assemble itself. These objects had done it in roughly 500 million years. Erica Nelson, an astrophysicist at the University of Colorado Boulder and co-author of the study, described the finding in terms that captured the disbelief of the entire field. She said, You just do not expect the early universe to be able to organise itself that quickly. These galaxies should not have had time to form. Her colleague, Joel Leyer of Penn State University, put it even more starkly. He said they found galaxy candidates as massive as our own Milky Way when the universe was 3% of its current age, and he called it astounding. The problem was not simply that the galaxies were large. The problem was that the mathematics did not allow them to be there. Building a galaxy is not a single event, it is a sequence. Dark matter has to accumulate first, then gas has to fall into the dark matter halo, then the gas has to cool, which requires time because hot gas resists compression. Then the cooled gas has to collapse into dense enough clumps to ignite nuclear fusion. Then the first stars have to form, burn through their fuel, and die, seeding the surrounding gas with heavier elements like carbon, oxygen, and nitrogen. Then a second generation of stars has to form from that enriched gas. Each step imposes a timescale that cannot be skipped. Each step depends on the one before it. You cannot build skyscrapers before you have poured the foundations. And the early universe was supposed to be pouring foundations. Webb found skyscrapers already standing. The researchers initially referred to these objects as universe breakers, not because they literally broke the universe, but because their existence strained the standard model of cosmology to its mathematical limits. According to Lambda CDM, the total amount of ordinary matter available in the universe at that time, combined with the maximum rate at which gravity could assemble it into stars, should not have been sufficient to produce galaxies of this mass this quickly. In some cases, the mass estimates implied that these early galaxies contained more stars than the available supply of ordinary matter could account for. The equations did not add up. Something was wrong with the timeline, or something was wrong with the equations, or both. The scientific community responded the way it always does when confronted with the impossible. It questioned the measurements. Perhaps the galaxies were not as massive as they appeared. Perhaps the light was being distorted by gravitational lensing, magnified by the mass of intervening galaxy clusters. Perhaps dust was making them appear brighter than they really were. Perhaps the instruments were miscalibrated. Every possible source of error was examined, and some of the corrections helped. A study published in November 2025 by Katherine Chorofsky at the University of Texas at Austin showed that some of the galaxies that appeared overly massive likely hosted actively feeding supermassive black holes. The friction of gas falling into these black holes generates enormous heat and light, making the galaxies appear far brighter and more massive than they would if the light came from stars alone. This reduced the most extreme mass estimates. The universe breakers became somewhat less extreme, but they did not disappear. Even after correcting for black hole contributions, the early universe still contained roughly twice as many massive galaxies as the standard model predicted. The tension eased. It did not resolve, and in August 2025, researchers at the University of Missouri, using Webb data, identified 300 additional, unusually bright objects in the early universe that defied explanation. 300 objects, not 6. The pattern was not shrinking, it was growing. The early universe was not empty, it was not dim, it was not fragile. It was luminous, crowded, and impossibly busy. And no one could fully explain how it got that way so fast. The galaxies were not the only impossible things the James Webb Space Telescope found in the early universe. Sitting at the centres of many of them, already fully formed, already actively consuming matter, already radiating with the ferocity of a billion suns, were supermassive black holes. And they had no business being there. A black hole is not complicated in principle. It is a region of space where gravity has become so intense that nothing, not light, not radiation, not information of any kind, can escape. They form when massive stars exhaust their nuclear fuel and collapse under their own weight. The core implodes. The outer layers are blasted away in a supernova. What remains is a stellar mass black hole, an object typically weighing between 5 and 50 times the mass of the Sun. These stellar remnants are real. They have been detected by the dozens through gravitational wave observatories like LIGO and Virgo, which record the ripples in space-time produced when two black holes collide and merge. But a stellar mass black hole is not the same thing as a supermassive black hole. The black holes at the centres of galaxies are not 10 or 50 times the mass of the Sun. They are millions to billions of times the mass of the Sun. The supermassive black hole at the centre of our own Milky Way, Sagittarius A star, weighs roughly 4 million solar masses. The one at the centre of the galaxy, Messier 87, the first black hole ever directly imaged by the Event Horizon Telescope in 2019, weighs approximately 6.5 billion solar masses. These objects are not just bigger versions of stellar mass black holes, they are an entirely different category of gravitational monster. The question of how supermassive black holes form has been one of the deepest unsolved problems in astrophysics for decades. The standard pathway begins with a stellar mass black hole, perhaps 20 or 30 solar masses, left behind by the death of a massive star. This seed then grows by consuming surrounding gas and matter. As material falls toward the black hole, it forms a swirling disk of superheated gas called an accretion disk. Friction within the disk generates extraordinary temperatures, sometimes hundreds of millions of degrees, producing intense radiation that streams outward in every direction. This radiation creates a problem. It pushes back against the infalling gas. The brighter the accretion disk, the harder it pushes. There is a theoretical maximum rate at which a black hole can consume matter, a limit set by the balance between the inward pull of gravity and the outward push of radiation pressure. It is called the Eddington limit, named after the British astrophysicist Arthur Eddington. A black hole feeding at the Eddington limit can roughly double its mass every few tens of millions of years. This sounds fast. It is not fast enough. Start with a 20 solar mass seed at the Eddington limit and ask how long it takes to reach 1 billion solar masses. The answer, even under the most generous assumptions, is roughly 800 million years. That is the absolute minimum. In practice, black holes do not feed continuously at the Eddington limit. Thus, supplies are interrupted by mergers, by feedback from the radiation itself, by turbulence in the surrounding medium. Realistic growth timescales are significantly longer, and yet, the James Webb Space Telescope has found supermassive black holes weighing hundreds of millions of solar masses already in place when the universe was less than 500 million years old. Some observations push this even further. In August 2025, a team led by Pablo Pérez González at the Center for Astrobiology in Madrid reported the detection of light sources at redshifts of 17 and 25, corresponding to an epoch when the universe was only 100 to 200 million years old. These are the deepest observations ever made by Webb. At redshift 25, the universe was roughly 100 million years old. The first stars should barely have had time to form, let alone live, die, and leave behind black hole seeds that could grow into anything substantial. And yet, there were sources of blue ultraviolet light, exactly the kind of light that massive first-generation stars or actively feeding black holes would produce, shining in an era that the standard model says should have been dark. The mathematics simply does not work. You cannot start with a stellar mass seed after the first stars form, feed it at the maximum theoretically permitted rate, and arrive at a supermassive black hole in the time available. The universe was not old enough. Something else must have happened. And the leading candidates for that something else are each extraordinary in their own way. The first possibility is direct collapse. Instead of forming from the death of a star, a supermassive black hole could form from the direct gravitational collapse of an enormous cloud of primordial gas. No star formation, no intermediate step. A cloud of hydrogen and helium, perhaps 100,000 solar masses, collapsing directly into a black hole in a single catastrophic event. This requires very specific conditions. The gas cloud must be warm enough to avoid fragmenting into smaller clumps that would form ordinary stars, instead of collapsing as a single unit. Ultraviolet radiation from nearby sources could provide this heating, preventing the gas from cooling and fragmenting. If the conditions are right, the cloud collapses whole, producing a massive seed black hole of 10,000 to 100,000 solar masses in a single event. From that much larger starting point, reaching 1 billion solar masses within 500 million years becomes mathematically possible, though still challenging. The second possibility involves the first generation of stars themselves. The very first stars that formed in the universe, called population 3 stars, are believed to have been radically different from the stars we see today. They formed from pure hydrogen and helium, without the heavier elements that help gas cool and fragment into smaller clumps. Without efficient cooling, the gas clouds that formed these stars may have remained massive, producing individual stars weighing hundreds or even thousands of solar masses. When these hypermassive stars exhausted their fuel and collapsed, they would have left behind black hole seeds far larger than anything produced by modern stars. Seeds of several hundred solar masses would have a significant head start on the growth timeline, potentially reaching supermassive scales within the available time. The third possibility is rapid merging. In the dense, compact early universe, where everything was closer together and collision rates were far higher than they are today, black holes may have grown not primarily by consuming gas, but by colliding with and absorbing each other. Two black holes in close proximity spiral inward, merge, and produce a larger black hole. That larger black hole encounters another, merges again. In a dense enough environment, this chain of mergers could build mass far faster than accretion alone. Gravitational wave observatories have already confirmed that black hole mergers occur in the modern universe. In the early universe, when densities were far higher, merger rates could have been extraordinary. In September 2025, another discovery added a new layer to the mystery. Astronomers using Webb data reported finding objects they called little red dots. These were compact, extremely red sources scattered through the early universe that did not fit the profile of ordinary galaxies or ordinary quasars. Further analysis suggested that some of these little red dots might not be galaxies at all. They might be an entirely new type of object. Black hole stars, theoretical hybrids in which a massive black hole sits at the core of a bloated, luminous envelope of gas, radiating with properties that do not match any known category of astronomical object. If these objects exist, they represent a formation pathway that no one had predicted, a type of object that was not in the textbooks until the James Webb Space Telescope forced it into existence by observing something that could not be anything else. None of these explanations has been confirmed. None can be ruled out. What is clear is that the standard story of black hole growth, the slow, steady Eddington limited accretion from a small stellar seed, cannot account for what Webb is seeing. Something happened in the early universe that allowed black holes to grow far faster than our models permit. Whether that something was direct collapse, hypermassive first stars, runaway mergers, or an entirely new class of object that we have not yet named, the result is the same. The early universe was not the dark, quiet, slowly assembling place we imagined. It was a factory, and whatever it was building it at a pace that our equations cannot explain. The impossible galaxies and the impossible black holes were unsettling enough on their own, but they were individual objects, points of light in a vast darkness. They could, in principle, be explained as outliers, statistical flukes, rare events that happened to form under unusually favourable conditions in unusually dense pockets of the early universe. The scientific community was willing to entertain that possibility. What made it untenable was the discovery that these objects were not scattered randomly through space. They were organised, connected, threaded together by structures so large and so mature that they should not have existed for billions of years after the era in which Webb found them. On the largest scales, the universe is not a uniform soup of galaxies drifting through empty space. It is a web. A vast, interconnected network of filaments, long strands of matter stretching tens and hundreds of millions of light-years, intersecting at dense nodes where galaxy clusters form, separated by enormous voids where almost nothing exists. This architecture is called the cosmic web. It was predicted by cosmological simulations decades before it was directly observed. The prediction was elegant. After the Big Bang, dark matter responded to the tiny density variations imprinted during inflation. It accumulated slowly, pull ordinary matter along with it. Over billions of years, gravity carved the initially smooth distribution of matter into the filamentary structure we see today. Matter flowed along these filaments like water through channels, feeding galaxies at the intersections, draining the spaces between them into voids. The cosmic web was supposed to take time, billions of years of gravitational work, slowly separating dense regions from empty ones, gradually building the scaffolding on which galaxies would eventually assemble. And yet, the James Webb Space Telescope found it already in place when the universe was still young. One of the most striking examples is a structure astronomers named the Cosmic Vine. Discovered in Webb data, it is a chain of more than 20 closely packed galaxies stretching over 13 million light-years. This structure existed when the universe was only a few billion years old, yet its scale and organisation rival formations in the modern universe that have had more than 10 billion years to develop. Several of the largest galaxies within the Cosmic Vine had already stopped forming stars. They had exhausted or expelled the gas needed to create new ones. This is called quenching. In the modern universe, quenching is common in massive galaxies that have consumed their fuel supply. But in the early universe, finding quenched galaxies inside an organised filamentary structure was deeply unexpected. It meant that these galaxies had not only formed quickly, they had lived quickly. They had burned through their entire supply of star-forming material in a fraction of the time that comparable galaxies in the modern universe would take. They were already old, already retired, already done, in a universe that was itself barely out of infancy. Using Webb data, astronomers assembled the deepest catalogue of galaxy groups ever produced. More than 1,600 groups and protoclusters spanning from roughly 12 billion years ago to just a few billion years ago. These groups represent the building blocks of today's massive galaxy clusters. The Coma cluster, the Virgo cluster, the enormous gravitationally bound structures that contain thousands of galaxies and weigh quadrillions of solar masses. Webb's catalogue showed these building blocks already taking shape far earlier than the standard model comfortably allows. By comparing groups at different distances, which corresponds to comparing them at different epochs of cosmic history, scientists could watch structure formation unfold across time like a time-lapse. Early groups appeared chaotic. Star formation was intense and violent. Later groups showed increasing order, smoother shapes, and slower growth as gravity settled into a more stable rhythm. This continuous view across billions of years of cosmic evolution had never been possible before Webb. In 2025, a team at the University of Cambridge published a study analysing more than 250 young galaxies using Webb's near-infrared camera spectrograph. By studying the internal motion of gas within these galaxies, they discovered that most were turbulent, clumpy systems that had not yet settled into the smooth, rotating disks that characterise galaxies in the modern universe, like our own Milky Way. The early universe was messy. Gas was being stirred by violent star formation, gravitational instabilities, and mergers with neighbouring systems. Galaxies were not gently assembling themselves, they were crashing together, tearing each other apart, and rebuilding from the debris. The Cambridge team found that galaxies gradually transitioned from chaotic to ordered as the universe aged. But the key finding was how early the chaos began. The turbulence was already intense when the universe was only 800 million years old. Something had already provided enough energy, enough mass, enough gravitational interaction to create violent internal dynamics in systems that the standard model said should barely exist yet. And then there was the big wheel. In early 2025, researchers discovered a galaxy with a fully formed spiral structure that existed within the first 2 billion years of the universe. This was not a fuzzy blob. It was a beautiful, organised spiral, with arms curving outward from the central bulge, resembling galaxies like the Milky Way that have had over 10 billion years to develop their elegant structure. The big wheel was massive. Its location in a crowded region of space suggested it had likely experienced collisions and mergers with other galaxies. Normally, mergers destroy spiral structure. They smear the delicate arms into a featureless elliptical shape. The fact that the big wheel retained its spiral form meant that either it had grown through an unusually orderly process, accreting mass smoothly without violent disruption, or there were mechanisms of galaxy growth operating in the early universe that we have never encountered in the local observable universe. Themia Naniakara of Swinburne University of Technology, one of the researchers who discovered the big wheel, captured the significance clearly. He noted that the fact that this galaxy did not become elliptical suggests there might be ways that galaxies can grow that we have not encountered in the local universe. This is not a minor observation. It is a statement that the rules we derive from studying nearby galaxies may not apply to the early cosmos. The universe may have had pathways for building structure that have since closed, mechanisms that operated only under the unique conditions of the first few billion years, when matter was denser, temperatures were higher, and the distances between objects were smaller. This is the pattern that emerges from every direction Webb points its instruments. Not a single anomaly, not a handful of outliers, a systematic, pervasive mismatch between what the standard model predicts for the early universe and what the early universe actually looked like. Too many galaxies, too massive, too bright, too chemically mature, too organized, too connected, too fast. The cosmic web is supposed to take billions of years to weave itself into existence. Webb found it already woven. The filaments were already there. The clusters were already forming. The galaxies within those clusters had already lived fast enough to exhaust their fuel and stop making stars. The architecture of the universe was assembled on a schedule that the equations say should have been impossible. And this raises a question that cuts deeper than any individual observation. If the universe built its largest structures faster than gravity alone should have allowed, then either gravity worked differently in the early universe than it does today, or there was something else, some additional force, some unknown mechanism, some hidden variable in the equations that accelerated the assembly of everything we see. Whatever that something is, Webb has not identified it, but Webb has made it impossible to ignore. The early universe was not laying foundations, it was building cathedrals. And the blueprints it was using do not appear in any textbook we have written so far. There is a boundary in the universe that has nothing to do with walls or edges or physical barriers. It is a boundary of information, a horizon beyond which nothing can ever be seen, not because there is nothing there, but because the light from those regions has not had enough time to reach us since the universe began. This boundary is called the observable universe, and James Webb is pushing closer to it than any instrument in human history. The observable universe has a radius of approximately 46.1 billion light-years in every direction. This number confuses people. If the universe is only 13.8 billion years old, how can we see objects 46 billion light-years away? The answer lies in expansion. When a distant galaxy emitted the light we detect today, it was much closer to us than it is now. Over the billions of years that the light has been travelling, the space between us and that galaxy has been stretching continuously. By the time the photons arrive at Webb's mirror, the galaxy that emitted them has been carried tens of billions of light-years farther away by the expansion of space itself. We are not seeing the galaxy where it is now, we are seeing it where it was, and the distance between where it was and where it is has been growing the entire time the light was in transit. Light is not crossing a fixed distance, it is running on a treadmill that stretches as it runs. Early in the universe's history, expansion was slower and light made steady progress. As time passed, expansion accelerated, driven by dark energy, the mysterious force that makes up roughly 68% of the total energy content of the universe. Some photons managed to reach us because they began their journey early enough, when the treadmill was slower. Others, emitted from galaxies slightly farther away or slightly later, will never arrive. The space between us and them is growing faster than light can cross it. Not because anything is moving faster than the speed of light through space. Nothing is. But space itself is not bound by that speed limit. Space can stretch at any rate, and beyond a certain distance, it stretches faster than light can traverse it. Those regions are gone. Not temporarily, permanently. No signal from them will ever reach Earth. No technology, no matter how advanced, will ever change this. It is not an engineering limit. It is a law of physics. This creates a deeply unsettling situation. The observable universe, all 46.1 billion light-years of it in every direction, is almost certainly only a fraction of the total universe. We know this because the universe looks essentially the same in every direction we observe. The cosmic microwave background is nearly uniform across the entire sky. The distribution of galaxies does not thin out toward an edge. There is no indication of a boundary, a wall, a place where the universe stops. This smoothness would be impossible if space ended just beyond our view. The universe extends far beyond the cosmic horizon, How far? No one knows. Some models suggest it could be hundreds of times larger than the observable portion. Others suggest it could be infinite. Either way, the vast majority of everything that exists is permanently hidden from us. And the situation is getting worse. Dark energy is accelerating the expansion of the universe. This means the cosmic horizon is not static. As space stretches faster, galaxies that are currently visible will eventually be carried beyond the horizon. Their light will be stretched to longer and longer wavelengths, redshifted further and further into the infrared, then into microwave, then into radio waves so faint and so stretched that they become undetectable by any conceivable instrument. From our perspective, those galaxies will appear to slow down, freeze, and fade. They will not disappear in a flash. They will dissolve, gradually, over billions of years, dimming into a darkness that is not empty, but unreachable. If expansion continues at its current rate, in roughly 100 billion years, every galaxy outside our local gravitationally bound group, the Milky Way, Andromeda, and a few dozen smaller companions held together by their mutual gravity, will have crossed the cosmic horizon. Future observers, civilizations that might arise billions of years from now, would look up at the sky and see a universe containing only their local cluster of galaxies, surrounded by absolute darkness. They would have no way of knowing that trillions of other galaxies ever existed. The cosmic microwave background, the afterglow of the Big Bang itself, would have been stretched to wavelengths so long that it would be undetectable. There would be no evidence of the Big Bang at all. A civilization arising in that distant future would construct a model of the universe based on what it could see, and that model would be catastrophically wrong. It would describe a small, static, isolated island of galaxies in an empty void, with no beginning and no history. And there would be nothing incorrect about their observations. Their instruments would be working perfectly, their mathematics would be flawless, but reality would be hidden from them by the expansion of the space they inhabit. This is why the era we live in matters. Right now, today, the universe is still young enough and expansion has not yet accelerated far enough to erase the evidence of its own history. The cosmic microwave background is still detectable. Distant galaxies are still visible. The expansion rate can still be measured. The cosmic web can still be mapped. The conditions that produce the impossible galaxies and the impossible black holes and the impossible structures can still be studied. We are living in a window of observability, a brief period in cosmic time when the universe is old enough to have produced complexity and young enough to still show its evidence. That window will not last forever, and James Webb is the most powerful instrument we have ever built for looking through it. In one of its most ambitious observations, Webb focused on a region of sky only slightly larger than 3 full moons placed side by side. For hundreds of hours, it collected thousands of individual exposures, patiently gathering faint infrared signals that had been travelling for billions of years. When those images were combined, the result contained nearly 800,000 distinct galaxies. 800,000 galaxies in a patch of sky most people would describe as empty. Each one is not a star, it is a galaxy. Each contains millions, billions, sometimes trillions of stars. Many host planetary systems. Many are rich in elements forged by generations of stellar birth and death. To display this single image at the same resolution as the famous Hubble Ultra Deep Field, the print would need to be more than 4 meters tall and 4 meters wide. A wall of cosmic history. And every one of those 800,000 galaxies exists inside the observable universe, the fraction we can see. The small, illuminated corner of a reality that extends far beyond the reach of any instrument, any signal, any photon. Webb has not revealed the edge of the universe. It has revealed that there is no accessible edge, only a horizon that recedes as we approach it, stretched by the expansion of a cosmos that is under no obligation to let us see all of itself. What lies beyond the horizon is not nothing, it is more. More galaxies, more stars, more black holes, more cosmic web, more structure, more history, more reality. All of it unfolding in silence, in regions that will never send us a photon, never answer a question, never confirm or deny any theory we construct about them. The universe keeps its deepest secrets not in complexity, but in distance. Not behind locked doors, but behind expanding space. We built the James Webb Space Telescope to answer a question. The question was simple. What did the universe look like when it was young? We expected the answer to be simple too. Small galaxies, faint stars, a dark, quiet cosmos slowly waking up. A universe in its infancy, tentative and fragile, taking its first uncertain steps toward the complexity we see today. We expected a baby picture. We got a crime scene. The early universe was not empty, it was luminous. It was not quiet, it was violent. It was not slowly assembling its first modest structures. It was already crowded with galaxies as massive as the Milky Way, powered by supermassive black holes that had no right to exist, organized into filamentary structures that should have taken billions of years longer to form, and populated by objects so strange that we had to invent new categories just to describe them. The standard model of cosmology did not predict any of this. The equations said the universe needed time. Webb showed that the universe did not wait. This does not mean the standard model is wrong. That is an important distinction. Lambda CDM, the framework that describes the universe in terms of ordinary matter, dark energy, and the expansion of space, remains the most successful cosmological model ever constructed. It predicted the cosmic microwave background with extraordinary precision. It correctly described the large-scale distribution of galaxies. It accounted for the accelerating expansion of the universe. These are not small achievements. They are the foundation of modern cosmology. What Webb has revealed is not that the foundation is broken, it is that the foundation is incomplete. The analogy is not a wrong answer, it is a partial one. Imagine you have a map of a continent. The map accurately describes the coastline, the major rivers, the mountain ranges. You can navigate by it, you can make predictions with it, but when you travel to a remote corner of the continent that no one has visited before, you find a forest that is not on the map. Rivers that flow in directions the map does not show. A mountain range where the map shows plains. The map is not wrong about the places it already described, but it is missing features that become visible only when you explore further than anyone has gone before. Webb is the expedition that reached the unmapped territory, and the territory does not look like the map predicted. The missing features are not decorative, they are structural. If the early universe formed stars more efficiently than our models allow, then the rate at which gas converts to stars under extreme conditions needs to be revised. If supermassive black holes can reach billions of solar masses in less than 500 million years, then the mechanisms of black hole formation and growth need pathways we have not yet incorporated. Direct collapse, hypermassive first-generation stars, rapid merging in dense environments, black hole stars. Some of these ideas existed before Webb. What Webb did was turn them from speculative possibilities into observational necessities. The data demands them. The old pathways are not sufficient. The new ones must exist. We just have not found them yet. And there is a deeper implication that extends beyond galaxies and black holes. The cosmic web, the largest structure in the universe, the scaffolding on which everything hangs, was already woven when the universe was young. Filaments stretching millions of light years, protoclusters already assembling, galaxies already quenching inside organized structures. If this scaffolding was in place earlier than the models predict, then the interaction between dark matter and ordinary matter in the early universe was more efficient than we assumed. Dark matter halos may have formed faster, gas may have cooled faster, gravitational collapse may have proceeded under conditions we have not yet modelled correctly. The entire timeline of cosmic structure formation may need to be compressed. Not abandoned, compressed. The events we thought took billions of years may have taken hundreds of millions. The universe ran the same program, it just ran it faster. This has implications for dark energy as well. The accelerating expansion of the universe, driven by dark energy, determines how much of reality we can ever observe. Webb has shown us that the observable universe is richer, denser, and more structured than we expected. If the observable portion is this complex, then the total universe, the vast regions beyond the cosmic horizon that we will never see, must be staggeringly more so. We are not looking at a sparse scattering of islands in an empty ocean. We are looking at the edge of a continent that extends beyond our vision in every direction. And every year, as dark energy accelerates the expansion, more of that continent slips beyond the horizon. The window through which we can study the universe is slowly closing. Not quickly, not on any timescale that matters to human civilization, but closing. Webb has given us approximately 20 years of operational life. Its cryogenic coolant for the mid-infrared instrument will eventually be exhausted, though the near-infrared instruments can continue operating far longer. During that time, it will continue to push deeper into the early universe, probing earlier and earlier epochs, testing the limits of what existed and when. Every observation it makes is a question asked of the cosmos, and so far, every answer has been the same. More, earlier, faster, bigger. The universe does not match our expectations. It exceeds them, consistently and by margins that are too large to attribute to measurement error. The next generation of instruments will build on what Webb has started. The Nancy Grace Roman Space Telescope, scheduled for launch in the near future, will survey vast areas of sky with a field of view 200 times larger than Webb's, mapping the distribution of galaxies and dark matter across cosmic time. The extremely large telescope, currently under construction in Chile's Atacama Desert, with a primary mirror 39 meters in diameter, will study the spectra of individual stars in distant galaxies, measuring their chemical composition and age with a precision that Webb cannot achieve. The Vera C. Rubin Observatory will scan the entire visible sky repeatedly for a decade, cataloguing billions of objects and tracking their changes over time. Together, these instruments will either confirm Webb's findings and force a revision of the standard model, or reveal the systematic errors that explain the anomalies. Either outcome transforms our understanding, but for now, in this moment, we are left with the data, and the data says something that is both humbling and exhilarating. The universe did not wait for our equations to give it permission. It did not consult our models before deciding how quickly to build its first galaxies. It did not check the Eddington limit before growing its first black holes. It did not read our textbooks on structure formation before weaving the cosmic web. It simply did what physics allowed, under conditions we have not yet fully understood, at a pace we had not anticipated, producing a cosmos that is richer and stranger and more urgently alive than anything we had dared to imagine. The James Webb Space Telescope was built to look backward through time, to see the universe as it was 13 billion years ago, to find the beginning of everything. And it found it. But the beginning was not the quiet, dark, slowly stirring dawn we expected. It was a blaze, a surge of creation so intense and so rapid that it challenges the deepest assumptions of modern physics. We asked the universe to show us its infancy. It showed us something far more unsettling. It showed us that even at the very beginning, even in its first few 100 million years, even before most of the stars that exist today had been born, the universe was already building everything. Already assembling structures of staggering complexity. Already racing toward a future it seemed to know was coming, with an urgency that our equations cannot yet explain. The universe does not wait. It never has. And the light it sent us 13 billion years ago, now arriving one photon at a time on the gold-plated mirror of a machine floating 1 million miles from Earth, carries a single, unmistakable message. You are late. We have been building since the beginning, and you are only now learning to see what we have done.